Did you guys figure out what is VGA? It looks good for you. Is there any question regarding it? Anish, do you have a question?
Is the code from last lecture on Blackboard?
Everything there.
Ah, I see.
Okay. So everything there, let me share with you. I already put for you. Haven't tried it yet either. You guys should try it. Come on, we spend time on it. Anyway, let me share with you my screen. Everybody ready for the Thanksgiving and time off? I'm tired. I'm sure all of you are tired too. Yeah, I know. I wish we have like a week or 10 days or something. Something. So everybody see my screen, right? You guys can see my CPP, right?
Yes.
Okay, Blackboard. Um, 3300. Course document, week 14. Supporting materials, VGA compressed with Vivado 2018.2, and that's dot rare. So that means you can use the WinRare for like unzip it. Then here's the UART's written C code that I told you. You can look at it and learn about how can you make something similar. And then if you go backward like this, you will just go in recorded lectures, and then you will find the lectures, the link for the YouTube of the previous lecture. So if you notice, in course document every single week you open, you will find recorded lectures, supporting material. You know what I mean? Some of them are empty, some of them it's not. It depends on if we already have a shared documents or not, right? Then you already have here labs, for instance. Those are the 7 labs we already have. And then you already have here the rest of the midterm. Here's the ECE2300 review. I give you the all documentation about the most important things for the 2300. And midterm too. And then the final will be here, soon. Okay, Luke? Any questions so far regarding any of the previous materials? Anything regarding the what's called the VGA before we start talking about the PWM and Xadc? Do you have any question? Anish, do you have a question? Okay. Now, we need to talk about the PWM. So the PWM, it's just like a counter, right? It's a counter comparing with counter, right? And that's it. And what we can do, let me open my Vivado 2018. How many of you tried the Vitas, the new version? Have you guys tried it? Yeah, this one. Yeah, I'm using the old one. It's not because I like to use the old one. It's because the computer is very old. But I tried actually to install it on my Linux. But because I use Ubuntu, it's open source, and those guys with Linux it takes time and so on. So pretty much I'm gonna switch it to different version of Linux. But when I have time, maybe after finals and finish grading and all of these things. Because I have a new project with National Security Agency. Anyway, so create a project. See, I said create a project, it took forever. Everybody see create a new video project thing, right? 1 second, somebody sent me a message. It's from Sandia Lab. Oh. Have you guys heard about Sandia Lab, by the way? How many of you heard about it? I won't see in the future a couple of you in working for Sandia Lab, by the way. That's one of the things I really like to see here from Cal Poly. They are very, very well-established research lab. And by the way, they are funded by the Live More Labs, yes. They're funded by the Defense, DoD, Department of Defense, DARPA, and all of these guys. So I wish I can see you guys actually one day, one of you or a couple of you work there. I have a lot of friends there, I can help you in. So project name, let's call it PWM ECE3300. Then XE7A AC Scheiße A TCES -1. Have you guys seen the PWM material I shared with you? Or you didn't have a chance? Huh? Did you see the material or not? Do you remember when we were sharing the material about, how can we use the PWM? Hello? Hello? Anybody here? Rohat, did you see the material? Yes, what I'm saying, is there some problem with my, my speaker or something, or my voice? I don't know. Just let me know, because I'm trying to fix this computer. So what I'm saying that, I already shared the material with you about the PWM and Xadc, and it was one lecture before, right? So my question, did you guys go through it or not? Okay. So anyway, let me drag it, because it will be easy for me. PWM. There was a lecture I made here. Excuse me. We went through the definitions and everything, but here is what I'm gonna do for you. So basically, we need a code here, and then we'll say create a design source, and this design source, it will be our PWM core. Let's call it PWM core. What type of signals we need? This is sequential circuit, right? So you need to have a clock, we need to have a reset. By the way, I'm not gonna throw it again, because I already told you this in a like separated lecture, right? So I'll just like make the programming quite in front of you. So here is the reset. Then what will be the input from your point of view? So the input will be the switches, right? So the switches will be giving me the duty, the duty cycle, the duration. So it can be counter, or let's call it duty, something, and that can be 1, 2, 3, 4, 5, 6, 7, whatever, Then we need an output. An output will be the PWM, right? Out. Let's go PWM, and that will be an out, and it's just a single wire. Okay. So if you look to this code, I need to see something actually. Yeah, you should be hearing me. Okay. Okay. Anyway, now if you remember, how it works. We just have a bit counter, and that's called our bit counters. Do you guys agree? And from there, we start comparing with the R bit counters, right? If you guys remember very well what I'm talking about. So I'm gonna open here another file to share with you, and from there we can start. So here I'm looking for the PWM. A second, and I'll be with you because I need to open the file. I don't see very well. Top display. Okay. Anyway, I don't want to waste time here, so gonna be here the interface. We need the rebel counter that it will be start counting with what size of the duty we need, and from there we can start moving forward. So we need to make an always block here, positive edge of the clock or positive edge of the reset, begin, end, and that will be our, let's call it our counter. From there, if reset, then what will happen. We will need an internal rig, and that will be size of the 7 to 0, and that will be our count. Then from there, we'll say this R count equal I made a mistake. What was my mistake? This 0. Then R count, it will be what? It will be 8D0. Then else, this counter, it doesn't need to have enable. Okay, so it's just counting for all the time. So gonna be here R count is equal to R count plus 1. That's it. This is the most important part. Excuse me. Then we will go into the comparator. So we need to compare between a value coming from the R counter versus the duty, which is basically the switches we need. And from there, we will be pushing the outputs to a different level. So we need to go ahead and say always block at. You can make it with clock, or you can make it without clock. You can make it combinational circuit. There is no shame on this. So I will show you with with clock. It has the same meaning of what is better for me to share with you the slides, so it will be easy for you to understand what I'm saying. So share again. You see my my presentation slide? Hello.
Yes, Professor.
Yes. So you see what I'm doing, right? So the R bit counters I built in front of you is this plus 1D whatever. This is the counter. And this is basically what is called R underscore counter. That makes sense? Now we are moving into a comparator, right? The definition of the comparator is comparing between the duty and the R bit counters, right? And the output will be going in a flip-flop. So this flip-flop combined with the comparison thing is what? It is literally the always block with positive edge of the clock. So these two guys together can be written in one always block with positive edge of the clock. Or the other way to do it is to make an always block combinational followed by what? Another always block with sequential. Do you understand what I'm saying? Everybody aware with what I'm saying or not? If you guys understand what I'm saying, can you please give me any feedback? Say yes. Okay. Just 2 people said understood. So what about the rest? Yes. Okay. Okay. Excuse me. Now, so I'm gonna switch back the screen so I can show you what I'm doing. So, extremely dark. Oh my gosh, begin, and I call this what? Comparator. From there, I would say if reset. What I'm expecting to have the PWM equal 1B0, but that will not be going through because this is a wire, and wire cannot be going into this as we said mentioned the type of data. So we have to go back on the top here and say called reg, right? Then say here else. Here the else will be the crucial part. Why? Because say if what? If um, um, r count less PWM. No, I'm sorry. R count less duty. What will happen? We will have reported output. So gonna be PWM is equal 1B1. Else PWM should be. And if you notice, I didn't put begin and end because it's a single line, right? That makes sense? I have a news for you. We finished. Somebody wrote something. Let me see what it is. What the heck was this shit? Alt H. So we finished. We have a PWM. Would you imagine? We have a literally PWM. Now we need this PWM to give us this fancy, lovely coloring thing, right? Yeah. So then you see it's really pretty much fast. And by the way, I built for just for fun, a little radar system using the smaller version of FPGA. I hooked it in the top, and then I built like a step motor, and the step motor was controlled by the PWM coming from the FPGA. And then I made like a kind of Visual Studio interface through the UART with this fancy radar system, and then the online will just go around, and when it will see like a metal can, it will go ahead and tell you, oh, there is an object. And you can see also here, I'm destroying my 3D printer and removing the motherboard, which is a microcontroller, and putting a new FPGA on it. So FPGA, it's something very interesting. FPGA, it's something, yes, an obstacle detector, yes. And I'm using the ultrasound, and I'm using stuff, and even, I got LiDAR, yes, and I'm using this one. I'm actually with computer vision these days for building anti-missile systems for drones. So you see, you can have infinity ideas. As students, you should build a lot of stuff because that will show. I don't know how many of you in favor of continuing study with grad school, or how many of you in favor of moving into industry. But I'm a person who really like research, so I would recommend everybody to go for grad school. But if you like also industry, you have to put in your mind now, since you're in the 3000 level, where you would like to end up, and this stuff it helps. Can Nexus PWM? Yeah, this is one of the good question chat. So the thing that you need to buy a gadget. It's called it's a kind of isolator, because you don't want also draw a lot of current out of the board, because that's an analog thing that is a sensor. So it's a PWM or PMOD. It's a PMOD. I can give you the name. It's very cool. I would love actually if any of you guys like to do any. Yeah, it's PMOD. Have you heard about this? I can show you. Stop. Open my chat. Then I do here search. Look. DigiLent. Yeah, because of the yes. So look at this. So everybody can see the DigiLent official website, right? Hello.
Yeah.
Okay, so look, we have ton of PWM. I have some here in my office. They give it to me for research, but it's like I have one for an easy light sensor. I have a GPS, so I can locate myself using satellites. I have single channel 16-bit digital to analog conversion, and I can build antenna on it. And then I have here the one you are looking for, temperature sensor accurate to within ±1 Celsius. And then I have another one, which is, I don't know, where did it go? I use it for extending the PMOD as a digital port for analog devices to be connected, like range sensors and all of these things. So you can find it like $20 or something. See, this is the GPS I was talking about. Here is a Bluetooth for people who are really interested in security. And also, here is the Pixel OLED displays. Even there is SD card extension. You can have more memory banks coming from the SD cards, and that will help you to put a processor like RISC-V processors, or the Boom processor, which have been developed by the UC Berkeley team. There is Wi-Fi interface. This is the one, no, there is one actually, I would like to show it to you, Shad. Where is it? I will show it to you 1 second. Here, look at this, Chad. It's just $4, the one that you're asking for. It's servo connectors. So basically, when you go there, you connect the PMOD to it, and from there you can communicate with the range sensors, whatever gadget you want. You can actually build your own robots using FPGA. And that's really quite nice because, you can send did you see this bit stream you send? You can send it through Wi-Fi. Then, basically you are changing the functionality of the robot from far distance. You understand what I'm saying? So there is fun you can do with FPGA, basically. Anyway, excuse me, I'm very sorry. Okay, anyway, if we look to this, I need RGB also because, this 3 LEDs we have, they have colors, right? We have 2 LED here. Can you see my camera? This 2? Where are they? Oh, Shiza, here. This 2. Everybody can see it, right?
Yes.
Yeah.
This 2 actually, they have 3 different colors. So you can have actually 3 different PWM core, and everyone will be responsible for color, and you play with the resolution, then you will mix a color. You know what I mean? That's one of the possible way to do. So basically what we can do, we can just say here, create, and then, from there, add file, and then we call this, I don't know what is this, I don't want to do it like that. I say X, create file, and let's call it top PWM. And then I'm expecting to have clock reset and then do UT red.
Professor, we only see your desktop.
Oh, you cannot see my, oh, I'm sorry. Well, that's another project we can do. We can extend the zoom and in a way that it's gonna make Zoom multi screens. There is a way to do it using Visual Studio and Python, but the problem we just have 24 hours. We don't have that much hours. What is the best way for you if you would like to have more hours in a day? What you should do to make it more than 24 hours? That's something I would say that's certain. If you are a person and you would like to extend the number of hours per day, what you gonna do? It's a physics. What you gonna do? You will wake up early. Wait. Drink coffee. No. You will design a machine that it will slow down the movement of Earth. So then you will stretch the seconds. Then that will be stretching the minutes and then hours. Then you can have more hours or more time. Right? Because other than that, still you will have a second day. No matter you will stay up later or whatever. But that's just fun. Anyway, so we have red, green, right? And then we have the other one, which is red, green, blue, right? Duty blue. Those are outputs, right? No, those are input, and we can just make them like that. And those are why you make it 7-bit? To make it 256 because the color red, green. No, maybe we can make it 3, 3, 3, so we can have less switches, right? So gonna be 4, 4, 4. So 3, 3, 3. Whoa, whoa, whoa. Oh, 3. What? Okay. Don't worry. Okay. Then we need PWM for red. We need PWM for green. We need PWM for blue, right? Those are outputs. That's it. Then it's better for us actually to go ahead and make what here parameter r size equal 8. -1 Makes sense. I made a mistake, and then later on, we'll figure it out together. I like to make mistakes for a reason. Anyway, so we take a copy of this, and we'll go here. And then, we'll have, of course, some issues. We'll remove this, and let's copy PWM. And that's PWM red. And we say here, dot. And then, we'll take this guy like that. And then, we take this clock, reset, duty, PWM. Okay, then we'll take this guy. What we are doing now, if you remember, it's called an instantiation, right? So we instantiate the R, green, blue. Then clock is master clock, reset is master reset. Clock, reset, clock, reset. Then the PWM, it depends on the name. So this is red, red. This is blue, blue. This is green, green. Then this duty R. This is the duty green. This is duty blue. Sounds good. Now we can just move this. Didn't mean that. That's one of the negative thing about, you know, the editor that, you know, came with Vivado. That's why I don't like using it. But anyway, now we're gonna be like that. Parameter. Parameter, and they're gonna be size equal 4. Okay, so we take this, we say size. And then, you know, take this and say size -1, size -1, size -1. So you guys are following what I'm doing? You understand what I did? Now, the thing that I all the time forget, which is what? The constraint file. So we'll just say here, add constraints, create, and then, you know, we call it what? We call it PWM. Just a name for name. And then from there, we open like this. And then, you know, we go our lovely XDC file from GitHub. Nexus X4. Copy. And then a copy. And then, you know, we go here. This guy is called clock. This guy is called clock. And then we need what? What we need? Somebody tell me. We need 4 for duty R and whatever, right? And then, you know, we need the, where is the color LED? We need to find it. It's under the LED thing, right? Here. Which one you guys prefer? The 16 or 17? Huh? 17? Okay. You know, because Mario likes 17, I'm gonna make it 17. Okay. Then, you know, I go here in the top. I take this copy and I say this is the red. And then this is the green. This is the blue. Then, you know, we need switches. So maybe what we can do, we need how many switches? We need UTR, it's gonna be 4, 4, 4, right? So 1, 2, 3, 4, right? So they're gonna be okay. Then, you know, we need 1, 2, 3, 4. Then that's gonna be 0, 1, 2, 3, and that will be what? Green, right? Green. Then we need how many? Blue, right? 1, 2, 3, 4. So gonna be here what? 0, 1. That would be like this. Red, green, blue. 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 Are we missing anything? Huh? Tell me. Eduardo, are we missing anything? Yes, reset. So where is our reset? We can take PTC as a reset. Reset. Anything else? Anything else, guys? Okay, in that case, we'll just, oh, scheiße. In that case, we'll just say, you know, generate bit stream and see what will happen. Sorry if it takes some time, you know. How many of you heard that, you know, AMD bought Silence? Have you guys heard this? Yes, here is a cool file. Yeah, they got them for like 30-something billion, right? I'm just really disappointed because, you know, ARM had been acquired by NVIDIA for $40 billion, and Xilinx less than that by $5 billion. That's really bad. I mean, I'm a big fan of Xilinx, so I'm really disappointed. Altera got acquired a couple of years ago by Intel for $16.7 billion. At that time, it was the biggest ever deal happened in the whole entire history. So that's really quite. Look at how many lookup table and flip flops. That's why, you know, we are not coding for coding. We are coding after we fully understand what is going on, the whole entire design. You know what I mean? That makes sense? My board is connected somewhere. Yeah. Excuse me. Yeah. Excuse me. How much power? 0.012. Yeah, not bad. Open hardware manager. Open target. What? What's this? Interesting. Okay. Weird. For unknown reason, this board is not working anymore. It seems that I destroyed it. Oh, 1 second. Yeah, that was working. Everybody can see it? This camera thing. So now I'm gonna flash it. Let's see. Shut. Look, guys, I don't know if how you're gonna see it, but everybody can see my board. If it's clear to everybody, yes or no?
Yeah.
Yeah.
Look what I'm gonna do now. I'm gonna use the reddish, right? So you notice that red is starting going, right? Red is going higher. Red is going higher. Red is going higher, right? So I made the maximum here. Look, I'm now involving another color. Look. So the other color came with the red, and the brightness went what? High. Let's say I'm gonna involve 1, 2, 3, 4, 1, 2, 3, 4. I'm gonna start pushing the blue. Look, the blue came in the middle. So everybody see what I did? Now you can play with an intensity, for instance, here and there. You know, now you got some purple, whatever, you know, some other stuff, you know. I mean, you play with in general. But by the way, be careful with your eyes because, you know, this thing, the intensity is really high. So is it clear? Yes, yes, because you know the whole entire thing, the 3 different colors from the XADC is basically you have a kind of digital to analog converter, and you are playing with the resistive of it, you know, and you know when you are mixing between of them, the new colors coming out, and then the intensity will be changing, of course. So watch out your eyes. Basically, you can actually make it even. You can make it counter to counter. Do you understand what I'm saying? Like, you know, you can mix 3 different counter running in 3 different frequency zone. Then you know the colors will be keep it changing by itself in a wide range of spectrum. Anybody understand what I'm saying? So I can show you this as just a fun example. So you know the same code I wrote here. I will make a little bit modification on it. You see that? What is this a little bit modification? No. We can make a new counter with loading system. So I'm gonna modify this in front of you. So what exactly I need? I need a load. So I need here a new signal called input load. Okay. Then I will need a new register, which is called duty load. R size -1, 0, and then you call it duty. Why I do it like this? Duty load. Then I will go into this and say always at pause edge of the clock on or pause edge of the reset begin end. Then I say f reset. What will happen? Duty load will be what was that size again? You know what? Let's be more tricky. Make it 0 like that, so it will be taking the whole entire thing. 0. Else, begin end this time, because you know we're gonna write some stuff in a minute. If load high, we need something, right? And what that's saying, it's gonna be loading the counter. So gonna be duty load going into the duty. Else, what? What was called? Okay. Let's get sensitive. Anyway, they're gonna be here duty load equal duty load +1. So you know what I'm doing here, right? So what I did literally, I built a counter with ability of loading it in a certain amount of time when the load signal come as an asynchronous behavior. Then that duty will be the one compared here instead of duty up. So gonna be there. So see what I did? So pretty much I'm asking the spectrum to be what controlled automatically from the initial point that you're gonna give it by the switches. That makes sense? You guys understand what I'm doing? Hello? Okay, so in that case, we need to go here and see what we added. We added load, so we have to go in the top here and we put here load. Load. Dot load. Done. Then we need to here and say input load R, input load G, and input load blue, right? I don't know why it doesn't like it, because it's semicolon, you know. My screen also is, the screen here on the right side is old, so it's actually affecting in my vision. But anyway, here are G. Then I don't know why it's mad, but we'll find out why it's mad.
You put a plus sign after the reset.
Oh, I told you this screen, you know, I have two screens in front of me, right? And this one is quite old, so it's like, you know, it's kind of blurring. So even affecting my vision, you know. Anyway, so now the whole entire thing is already what? Cleared up. But, you know, we need to add this load thing. So we'll go and maybe make it in the bottom here. How many loads? We have 3, right? So 1, 2, 3. And, you know, we can go here and say load R, load R, load G, load B. And we can just go ahead and just say generate bit stream. So, you know, this is one of the disadvantage of FPGA, that every time you have to run synthesis, right? And but then, you know, there is something in Verilog, or not Verilog, how do description languages in general, called overlay architecture. So you will build like a wide range of reconfigurable IP, and from there the software will be changing it momentarily, like in a runtime, and you don't need to run synthesis every time. But this is beyond the scope of the 3300. Okay, I mean, I don't want to overwhelm you with a lot of information. So is it clear what exactly I have done here? Anish? Yes. Ashley, is it clear? Okay. See, I increased number. See, just for this trick, I increased number of lookup table and flip-flop to 19 and 17. So that show you that little bitty, itty bitty tiny changes can cost you more resources, right? So you have to be really wise while you are doing the movement. Power increased by 0.001. If you remember that number, it was 0.102, right? It's just like a little bit fraction. Now open hardware manager. We'll just like reset the CPU here and program set reset. So basically, we return it back to the demo thing on the flash. Say auto and program device. We haven't loaded anything, right? Everybody see my thing, right? So I'm gonna say that I would like to make my starting point 7, for instance, for the R. 1, 2, 3. Then from there, I will ask the responsible switch to load it, right? So what was the responsible switch? Is basically R. It's the third one in the line, so this 1. So I load it now, right? Then I will just go like this. Look what will happen. So because we are running in 100 megahertz, your eyes will not recognize that there is a changes in the brightness. You guys understand what I'm saying? If you go down blue to a certain amount of time, I mean the maximum frequency, yeah, what will happen? This thing, it automatically will keep it changing colors, because you made different values, starting values, and you're asking thing to be changing. So this value will be go like this, like less intensity, different colors, and then high intensity, different color. I see. Normally what I told the students before, you have to bring like a piece of paper and you put it on the top of it, so your eyes will be able to recognize it. So I would recommend for us to go ahead and say add power clock here. So what we can do, excuse me, IP catalog. Clock. Wait. Takes forever. Oh my gosh. PLL. Let's make the maximum frequency 10. Let's go even beyond 10, 6. No, it actually doesn't work on 6, 7. Then we'll go here and say active clock. Okay. And we just say generate. Okay. I said generate what? Okay. Say background. And then we're gonna top. And you're gonna instantiate the clock. So that means we need a new we call it wire. What? We call it wire. Yes, wire clock slow. Wire clock slow clock locked. It takes some time. So let's see what will happen here. So that guy is called what? It's called clock whatever. So I think let's copy. I'm going to copy here. And here, and let's call this, you know, clock gen slow. And from there, you just say here dot. And this is the output, so we call this clock slow. Let's make the reset the official reset we have. Wire lock. And then, you know, let's have this lock. Dot. And you put here lock. And then, you know, we have this and the dot clock. Okay. Yeah, exactly. It is clock divider thing. It is completely clock divider thing. And you know, it doesn't matter where exactly gonna be in the code because it's a parallel language. So you know, you're gonna come and say clock locked, assign clock locked equal clock slow ended with what? With lock. And we mentioned why we have done this many times. So here copy. Let's copy. And let's see what will be the reason, the thing that you know it will be coming. Everything now is under the hierarchy of the top PWM, so everything looks good. So if you scroll here, look, I want to show you something. Do you see this? Have you noticed? This is our design. PWMB, it took 11 of the resources. This one 11, and the PWMR took 20, and this because it's master basically. And then the total will be 63 cells. Need to find a piece of paper so you can see. One second. Oh man. Also, 4-bit is not enough for making fancy resolution. There's another trick I will show you as well. I'm trying to play with you all of Xadc because, you know, sorry, the PWM, because this is very interesting and very important for you. Okay, so we're gonna do this, and then I will make another experiment, and after that I will go through the theoretical part of the Xadc. And then, you know, do you guys like to have a lecture on Monday, or you don't want to have? Which way you prefer? Who's in favor of having a lecture on Monday? If we don't finish the Xadc, we can just do it. Yeah, you can ask, of course, you know. That's why I'm here, you know. Anyway. Easy. Is it better? Is it better, or should I remove the piece of paper? And then, you know, see, it keeps changing by itself slowly, you know. One of the other trick. Oh my gosh! See, you know, it started to get what? Look, I'm gonna make a trick of filter. Look at this. There is a different colors coming. Like there is reddish in the middle. Yeah, I see it. See, I see red here. Anyway, the other trick we can actually apply here, which is even more fun, is to go in this top file, okay, and no more duty R, G, and B, right? We can be more tricky. We can just have one like this. Look, and we call just duty, and this duty is gonna be what? The whole entire switches. No, instead of 13, we need 3 switches for the RGB, right? For load system. So what we can do, we can remove 3 out of 16, so we're gonna have 13. So it's gonna be here 13. You guys understand what I'm doing? Shad, is it clear? So for the rest of you guys, do you understand what I'm saying now? Why this will happen? Because we have 3 different loads for the 3 different counters, right? So we can actually trick it one by one, and all of them sharing the same input, and that will be kind of optimization as well. So, you know, you go into the Xadc here and say, you know, no more like this. It's gonna be here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have one control for the brightness essentially. Yes, 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 yes. I will show you. But then, you know, those guys will be loading, right? Because if you push the load R, so that means you are talking about the value written in the switches is dedicated for the R. It's not affecting on the B and G, right? Then, you know, you will done with R, then you will start doing the same thing. So you are doing something called time maxing. So you are actually spending more time manually than everything will be automated. You understand what I'm saying? You're playing with the whole entire thing. Just show that the circuit in general, or, you know, working in circuit design, it's a trade-off, you know. So we just go here and say no more R. And let's try and see what will be the effect. Number increase, of course, because the resolution of the count itself get bigger, right? We are using 13-bit. That makes sense? But in general, we don't need 13, right? Because the RGB, it's a range of 0 to 155, right? So you just need 8-bit each, right? So, why I'm doing this step by step, I'm not giving it to you one shot. So, you will start thinking, oh, he meant this, oh, he meant that, this is my way actually of teaching, it's like, open discussion by everybody will have it, and you don't need to be like completely moving and say it has to be it has to be it. It's based on it's some numerical things. It's 0 to 155. We're talking about 256 for each color. Then you will combine them together. You will get the whole entire number of things. Yes, when we put it in the board, it exactly. Yes, good. We have an error. Yay! I like errors. Why errors? It doesn't like duty. 12. What happened with 12? Yeah, we didn't have 12. Correct. He is right. See, that's actually called physical error. That's one of the mistakes you can get into it, because the Verilog is very relaxed language. So simulation you will not see it, but when you will go into the real implementation, you will cause you losing 5-6 minutes of synthesis. But VHDL, it's a hardware description language as also Verilog, but it had been made and developed by U.S. Air Force. They call it the baby of U.S. Air Force. So that's why most of the defense contractor like VHDL. Most of the civilian industry love Verilog. You know what I mean? So if you would like to work as a defense contractor, just hit into VHDL. If you just would like to be Intel guy, IBM guy, Linux, Verilog would be fair enough. Okay. Plus Verilog, when you are running it, you might get some warnings, and you don't know whether these warnings are really useful warnings or not. But in VHDL is more systematic language. So in a way that if really anybody tiny warning happening, it will give you a bunch of headache to resolve it. Yes, it's worth at the end of the day. Is it clear? Now, let's try it. So it's in front of you is off, right? Just a random number, right? I push here red. And then, look at red. Everybody see the red? Then I go like this. Say I need. Now I push what? A new value, which is for the green. Then I push something else, which is blue. Everybody see what happened? Hello? See, I went from the starting point, now is running fast. So it turned to be what? Different what? Color. Is it clear? Hello. If you want, you can even decrease this maximum frequency to a very low maximum frequency. You can make it in kHz. Okay, you can just make this, and then it will be all more and more recognized by your eyes, of course. Sounds good? Any questions so far? Is any question? Any questions? Anything is not clear? Content is not clear? We'll still be doing the Xadc today. It's up to you guys. Do you like me to do it? I can just show you at least the info about it, and then next time we can just can implement. Implement it will take 5 minutes, but anyway, stop sharing here. Let's go for Xadc. Here the Xadc. Okay, and then I can share with you my screen. Stop sharing. Can you see the Xadc, or you see still the Vivado? Wait. Xadc. No. Now is Xadc clear to everybody? You can see it, right? Okay. So, what is Xadc? So we have a dual Xadc on the Xilinx board. Okay. And you can see we have an analog part and a digital part. So here, dual ADC is a 12-bit resolution. It's a big resolution, by the way. And it's have 100 mega samples per second. Okay, so you can take 100 mega samples pieces per second using this Xadc. And there is one ability is for the differential input, and maximum swing between up and down is going to be 1 voltage. And there is some sensors on the board will be interested in, like die temperature, score voltage, and stuff like that. If you would like to monitor the temperature on the board, you have to use Xadc. Okay, and if you would like to monitor the voltage variation, you can also use the Xadc. Then it's analog multiplexer. It's not digital multiplexers. And there is actually the software side is a 64 times 16-bit control registers and some status registers, which is showing you what you can do and it changed based on the digital side for the analog side. Internally, what we have, the 2 mux of the analog here, bunch of inputs you cannot touch by your hand is internally. One of them is a temperature, voltage, all of these things belong to the die. And some externals, which is connected to this PMOD, specifically is called Xadc PMOD. You can see it on your board, right? So one of the ADC you cannot communicate with unless you will just make some selectors here using the the register control registers. So you will be able to exclude this on-chip temperatures and voltage and pressure, and you will just take something out here from the PMOD, and then you will go into the status registers, which is basically 64 registers, each one is 16-bit resolution, and then you will go into the DRP interface. So far, so good. Now, whatever I mentioned is basically what is written here. How are you gonna do it? It's pretty much straightforward, easy things. It's a IP. It's an IP. I'm gonna go through it, then I will just initiate it in front of you on the what's called Vivado, and then next time I'll just run you an example. That's it. So here is you're gonna go in the IP. You are looking for Xadc. Then you will go inside the Xadc. You already have the DRP, or you have an XE4 or none. What is XE4 if you communicate with processor and using the bus? This one is a standalone Xadc. Then you need it gonna be channels or the single channel or independent or simultaneous selections. Pretty much use the channel sequencer. Okay, then you have a reset signals for making reset for the whole entire thing. After that, you will go in the continuous mode and you will just check some gain and things. It's basically for the analog part of the Xadc. You don't care too much about it. Then you will go ahead and check the alarm. So basically, this Xadc is a little bit crazy. So if you would like to say that my temperature, if the chip will be high in temperature, give me alarm, noise, or LED turning on and so on. So you can set up here this. I don't need it. So you can just remove it. That's why you remove this signs. After that, you already have the bunch of the channels that we were talking about, the temperature, the voltage, some other internal thing, and here's the auxiliary. So the auxiliary is basically the one we're going to be communicating with outside. Okay, and here is the thing. And after that, where is the PMOD we are talking about? That's actually our lovely PMOD. Do you see my cursor? Everybody can see my cursor? Hello? Yes, it's yeah, it's in the top nearby this guy here, number 10. Yes. Then this is internally it's telling you which one is what because it's dedicated. By the way, the one who made this is not Xilinx. Xilinx built the chip. The one who made the board is Digilent. So Digilent actually fixed them. So if you would like to communicate with the auxiliary channel 3, you have to be looking to this specific pin in the PMOD 10. If you would like to talk to the auxiliary 10, you have to look to the sequence of the pin on the PMOD. You move forward to the 2 and you move forward to 11. And the last 4 is basically the VCC and ground, which is basically powering up the Xadc. Then internally, what we're gonna do is basically making a wrapper around the Xadc, so it will help us to start producing outputs on the 7-segment display. Or, you can make UART communications, or you can even build the circuit in a side with the potentiometer. And when you change the potentiometers, you push it into the Xadc, the values will be flickering on the 7-segment display or VGA or whatever, right? How you're gonna do it is basically like that. There is a bunch of in and out. You have to communicate with them and you take care of them. The rest of the controllers, you don't need to do it, but this is basically what you need to do exactly. That's a circuit one. As you are the only way to receive digital number from the X8 on the board. I mean, there is a bunch of communication protocols here. There is Ethernet. You can do it with what's called with Ethernet. But Ethernet, if you build a IP for it, it's very quite painful. That's why we use a processor for handling packets. Or the other side, which is basically the yeah, the other side is basically using the UART, yes, on this Nexus 4. If you would like to push data from the computer to the board, yes. Or you will send a signal using analog and convert it to digital, and you can build your own communication. It looks like they were Digilent. I mean, yeah, it is Digilent because Digilent built the PCB, right? But the one who built the chip is Xilinx. Xilinx made more channels. Look, you have a ton of channels, but who tied the channels for the external world? The PMOD Digilent. So you already have a bunch of others. Anything is not auxiliary, you cannot touch, of course, because it's internally. It's belong to the health of the chip. And here is a bunch of the status register I was talking to you about it. Look, this is all of the status registers we have, and it's telling you which number, when you write it, you will get it into the output as a status registers, and also the 64 16-bit read and write registers, as I told you, in a control. And then, it's basically communicating with the FTDI. One of the nice example we can do is basically potentiometers here. And then, we connect the head of the potentiometer to the pin of the positive on the PMOD and pin of the negative on the PMOD. Yes, correct. It is. You can get it from here. Yes. But anyway, and you know, based on this equation, you play a little bit, and you'll see the digital representation on the 7-segment display. Okay, and I have a ton of references for this coming from the Xadc manual from Xilinx, FPGA examples by Pongshu, and you know, bunch of other articles. And you know, my one of my senior projects, control project, which is have been selected by the showcase of College of Engineering 2 years ago. Any question regarding the theoretical part? Any question? It is, because you know, I put it with a PWM. You remember? Yes, PWM, and then you know, I follow up by Xadc. Look, it is very clear. Honestly, it's a piece of cake. You know, I can show you now if I say stop sharing, and then I say share, and then I go into the no, stop sharing again, and I say share, and then I go into my code. Right? If you close this, do you need the PWM? Do you want me to put the PWM for you on the in the material? Should I put it? Hello? Yes, I will do it for you. Sure. Anyway, you know, if you say close, everybody can see my Vivado, right? And then I say close project here. Yes. And create a project and say here XADC project ECE3300 ECS. Add source. No, we don't need a source. Just IP at catalog, and then you say Xadc. We're gonna follow exactly the same thing I mentioned in the slides, you know, and I show you how it is basically easy peasy lemon squeeze. Here is the Xadc. Everybody can see what I'm doing, right? I click here, and what I told you, you're gonna go into the, I want a DRP, and I told you there is multiple things. Single channel, that means one channel is communicating. I think it's better for you to go in a multiple channels. It's gonna be channel sequence, and then you know, you reset. You know, you're gonna be in a continuous mode and all of the things. Then you know, you go ahead. You're gonna communicate it with. You need this. You need enable. You leave it there, and you know, VPN is maximal channels. And then you know, you go in the alarm. I don't want any alarms. It's useless for me, because you know, I don't want to see that. I don't want to watch your resources. Then I need to go in the channels here. What the channels you would like to present? Maybe I would like to see the temperature. I would like to see the VCC input, as I said in front of you, and I don't want the VPN. I don't want this. And then you know, maybe I can try to turn all of my auxiliaries that I mentioned in the PMOD, which is basically 2.2 and 11.11, I believe, 2 and 3 and 10 and 11. That was the only thing connected with the, so 2 internally I'm gonna do, and basically 4, basically this is PNN, this is PNN, so that means 2 channels will be communicating with me. Okay, then I would just go ahead and say, you know, summary. The summary is giving me, as I told you, it's gonna be 100 megahertz, gonna be continuous. We're not gonna communicate with the XC, and they're gonna be channel sequencers, and it follows like this, and say yes. Then I say generate. Excuse me. Funny. If you open, see what we have. Somebody tell me. Look. We have those, right? Hello. And that's exactly the thing that you are seeing in front of you is basically the one we have here. Do you agree? So you have, you know, VBEX and 2, 3, channels, and you have the BASI, you have all of this. We have to communicate with them and, you know, make our wrappers exactly as I'm talking about. And you already have here the decoding circuit. The decoding circuit, it will take the channel out, 5-bit, and you have to tell them, you know, what type of register's number is. And from there, you will be able to represent it outside using 7-segment display, or you push it to the UART back to the computer, or whatever you want. If you want, I can make an example running with you next lecture. Sounds good? Okay. Clear to everybody? Did you guys learn anything out of this lecture today? If something difficult, please let me know. Yeah. I mean, it's not too much material, you know, this is basically a learning curve, right? Yeah, that's fine, you know, but at least, you know, I want you guys to focus more on practicing. Okay? If there is something is not clear, please let me know and I am here to help. Is there anything clear? Is there anything is not clear? Any questions so far? If there is no questions, I can say now it was no question. Material is very cool. Thank you, appreciate it. So in my, you know, from my side, I would like to thank you guys for the time and the effort that you're spending with this course. And it was my pleasure to talk to you guys, and happy Thanksgiving, everybody. God bless you and stay safe. Okay. I'm gonna post this by 8 p.m. today after I finish all of my teaching load. Okay. Have a wonderful day. Stay safe. Okay. God bless you.
Professor.
Even Professor. Thank you.
Thank you, Professor. Have a good Thanksgiving.
Happy Thanksgiving. Thank you.
Actually, Professor,
Yes, sir.
I wanted to ask you, what FPGA board would you is there an FPGA board that you would recommend more than, I say, the Nexus for DDR for like long-term use?
Yes.
What board would that be?
Something with ARM processor. So basically like Ping Z2.
A Pink Z2?
Yes.
That's the name of the processor, no?
You
Or
know,
the board?
let me share it with you. So I have a couple of them in my office. So
What are your thoughts on the microset? Is that a good board for?
yeah, I mean, I do. It's not teaching. I do it for my research. So
Yes.
yeah, here, look. Mm. Can you see my thing?
Yes.
Yes. I use it for senior project and stuff like that. And, you know, I need to build some IoT cluster for computation, but I don't have time. Maybe in break.
So the Pink Z2 is what you recommend for long-term use or like
Yes.
versatility.
Yes.
What processor does it have? Or
It's an ARM processor. So let me show you. Spec.
a Linux ARM processor?
Linux processor. Yeah, it should be
Ah.
Linux. Look, it has 512 mega micro SD, HDMI output input ports. It has here. It has Arduino headers as well. It has a Raspberry headers. You know, you can communicate with everything. You know, and the device here is Zinc whatever, which has an ARM processor.
Okay.
Let me show you.
The Zinc is the ARM processor?
Yeah, it's called SoC, System on Chip. Wait. Here, it has an ARM Cortex A9 dual core processor operating in 650 megahertz. Can you see it?
Yes, I see.
And then it has storage as this amount, DDR3, quad SPI flash. If I had time, I would tell you the SPI thing. By the way, the XADC and VGA, it's above the syllabus, but I'm giving it to you because that will help you also for the future work. And USB, Ethernet, power, audio, video, switches, expansion connectors. It has a lot of stuff. It's really good for like a couple of years for you for learning curve.
I see. Okay. And then this one is more based on if you want to add more, you would use the PMODs that come along with it.
Exactly.
And
And even you can get here PMOD expansion. PMOD expansion. Can you see with me PMOD expansion? We can find it. There's another adapter PMOD. And I've seen it. There's PMOD expansion, but I don't know where is it. I think this one, right? Adapter PMOD. Those are the big lists. I don't know. Sometimes they remove stuff. But also one of the things that's imagine, you can take one of the PMOD. Look at this. I'm looking for something. Where is it? You know what?
So taking one of those PMOD expansions, I could maybe like add whatever. So like I could add more dip switches compared to just the two or more LEDs. Yeah.
Yes, sir. Yes, sir. Like this. Look, like you build a calculator with PMOD and then push like a switch key. You can do a lot of crazy stuff. But now I need to find the. Wait. For instance, you can put here and you can have VGA. And he put in shouter or whatever, rotary encoders, stuff like that. Kuduk?
Is the ARM processor the same as what the soft processor on the FPG? Like
No,
for example, like the Microblaze is the Microblaze an ARM
no,
processor?
no. Microblaze is using Fabric. Yeah, Shad asked it for something, right? He left?
Yeah, he asked, isn't the board capable of reading
Yeah,
Python?
it ran Python, yes.
So the Microblaze and the Zinc aren't ARM processors.
Yes.
They're soft processors, right? That's the correct term.
So Microblaze is a soft processor. ARM is an ASIC processor. It's like a fixed processor on a chip.
Okay.
But when you say Microblaze, it's something software you're gonna use the VHDL and Verilog to build, or it already have been packaged as an IP on using Vivado Vetus, and you just deploy it on the resources on the chip.
Oh, I see. So, it's called a soft processor because it's made through software.
Exactly.
Oh,
Bunch of
okay.
switches.
Okay. So, and then an ARM processor is actually a physical one.
Yes, sir.
Oh, okay.
Okay.
I see. All right. Thank you, Professor.
Thank you, guys. So have a wonderful day. Happy Thanksgiving, and stay safe. Okay. God bless you.
For sure.
Thank
All
you.
right.
Bye.